But how does science work? Well, the entire concept of science entirely works only if it is reproducible. So what do I mean by reproducible? Suppose I say today that if I take a balloon, I try to blow the balloon up by inserting air into it. I blow air into it with my mouth, and then I say that there comes a time when if I blow any more air, the balloon bursts. Suppose I say this. This is my experiment and observation, and I explain it by saying that when I push a lot of air inside the balloon, the pressure due to the air molecules inside the balloon overcomes the atmospheric pressure on the outside. That is my standpoint, my viewpoint to explain this phenomenon. Fine. Now, is this scientific? How can we explain, how can we deduce that it is scientific or not? If this same experiment is repeated by a number of people from different geographical regions over a period of time, over a span of time, and in each time they find that yes, if you blow a lot of air into a balloon, it does burst, well, then it is science. So what I'm trying to say here is that science is not something like a miracle or magic that happens only once in a blue moon. It is something which is reproducible, something which you can do time and again, and each time it will produce the same result. That is how science works. Now, in the last class we were talking about astronomy. We said that how I believe, and also almost all the scientists believe, that astronomy is the oldest form of science. Maybe when it was actually being experienced or practiced by this men whom we call our forefathers, it did not have the name astronomy, but still we believe that it is one of the oldest forms of science. But there are other branches of science as well. Science often finds a new branch through the way of technology. Here we can take the example of something known as thermodynamics. I don't know if you have heard about this term, but thermodynamics basically has got to do with things that are related to heat and temperature. So in the early 18th century, well, it's pretty funny, but during that time, in the early 18th century, scientists had already discovered that how a planet moves around the sun, in which path it does, what is the nature of the path it follows, or what's the magnitude of the force between the sun and the planet. That was properly deduced to accuracy. But if you asked a scientist that if I take a beaker, if I take water in the beaker and I start heating the water contents inside the beaker, what is exactly happening to the molecules of water inside the beaker? The answer was not known. So we knew what is happening far out there in the celestial sphere, but in our home what's happening, that was unknown to us. So it is during this time that the field of thermodynamics emerged, partly because the steam engine was discovered by James Watt. So after the discovery of the steam engine, the field of thermodynamics started, it broadened, research in this field increased. So this is one way where we find one example where technology brings a new field of science into the forefront. One of the great virtues of studying physics is that physics always believes in something known as unification. Unification. It tries to unify things. It tries to find out that what is the common underlying principle. Take this example. There are two bodies of masses m1 and m2. What is the force acting between the masses? It is the universal gravitational constant times the product of their masses times their distance squared. Consider two charges, say one positive, one negative. What is the force of attraction between the charges? Because they are unlike, they will attract. It's 1 by 4 pi epsilon naught q1 q2 by r squared. You see, there is a wonderful similarity in the form of these two equations. Both of them are measuring force. Both of them have got a constant. Here g is the constant. Here 1 by 4 pi epsilon naught is the constant. Both have got a product of two masses. Here the two masses and here the two charges. And both of them inversely varies with the square of the distance. Such a wonderful unification. At the same time, physics also looks into something known as reductionism. So what is this reductionism? As I was saying, you have a beaker. Inside the beaker there are these water molecules, and you heat the water molecule from below, the entire water content. Now what is happening when you heat these contents? Well, you know it to some extent, that if this is a molecule of water, when you are heating the water molecule, what is happening is that the temperature of the water molecule is increased. As a result, the kinetic energy of the water molecule is increasing, and as a result, the water molecule starts rapidly vibrating. The exact way how these molecules behave can be studied with the help of statistical mechanics, and just by knowing how the individual molecules behave at the microscopic level, you can deduce, you can predict that what is going to happen to the entire water content at the macroscopic level. This is reductionism. So physics believes in unification and also reductionism. It wants to look into all the different branches of physics, all the different kinds of phenomena, and try to see if there is a common underlying principle. At the same time, it tries to look into a substance, into a phenomena, deep within it. It wants to understand what's happening at the ultimate depth, at the most fundamental level, and then tries to find out if that can express, if that can explain what we observe or feel at the macroscopic level. Well, measurement plays a very important role in physics. When you are measuring something, when you are actually performing experiments, that is when you can finally prove whether your hypothesis, your assumptions, your theories are correct or not. But there are again certain areas which we cannot prove. Like we all know that the speed of light is 3 times 10 to the power 8 meters per second. But no one knows why. No one can prove why it has got this particular speed. Why not 2 times or 4 times 10 to the power 8? So these are certain empirical truths with which we have to live. But then we must remember that we have come a long way. Starting from our journey as the hunter-gatherers of the caveman, we have come to this particular society where we send satellites, just like we are sending gifts to our neighbors, and we can access internet, we can access GPS all at our fingertips. But believe me that physics, you cannot pursue it alone. It is connected with all the other branches of science. So if physics is the English literature, then mathematics is the English language with which it is written. So in order to understand physics properly, you also need to understand the mathematics. You need to understand chemistry. You need to understand biology. Physics is connected to all these branches of science. Take this example. Suppose you go to the kitchen and you want to brew a perfect cup of coffee. So what do? You take a container, you pour half a glass of milk into the container, you boil it. In another container, you pour half a glass of water and you boil it. Then you mix them together, you add a teaspoon of sugar, a teaspoon of coffee, you stir it well, and there's your coffee ready. But in this simple mundane process, just imagine how many scientific phenomena are taking place at the same time. When you're trying to boil milk or you're trying to boil water, what is boiling? Why does a substance boil? Or for that matter, why boiling happens? What is happening at the molecular level, as I said? How is that increase in temperature leading to an increase in kinetic energy, which is making it jiggle more vigorously? As a result, it's jiggling and going to hit the other neighboring molecules, which jiggle even more rapidly. They hit the walls of the container, and there is an entire catastrophic collision taking place in that small container, which you are seeing as the boiling. Once the substances are boiled, you are pouring it into glass, then the things mix. How substances mix is something that deals with chemistry. You need to know about the dipolar nature of the water molecule, the hydrogen bonds holding the hydrogen and the oxygen atoms. That's something related with chemistry. And then once that perfect cup of coffee is ready, you can smell it. How do we smell something? What is there in the receptors of our nose? The olfactory nerve endings that are present inside our nose. Well, in order to understand that, you need to know biology. But again, for the nerve endings, their axons and the synapses of the two nerves, when they connect, there is this neurotransmitter, which is a chemical molecule, acetylcholine, working at the most fundamental level. And what are nerve impulses? Electrical signals. That's physics. So you see, everything is connected with each other. In order to truly understand the flavor of this subject, you also need to study the other related branches of science properly. Only then you can deduce, you can extract the best nectar out of this flower.